All right, so here we are with the strong acid, strong base graph, okay? And I'm asking for a few different things here listed. And the first thing is determine the concentration of the acid. Okay, well, I'm going to start that right by finding the equivalence point. And how I do that, party people, is I am going to find the place on the graph where the hydroxides that I added from the base equal the protons in the beaker. So knowing that, and then this is not very smooth, but knowing that there's really an asymptotic line that occurred here in this this titration curve. This one didn't really show that too much, but these lines are usually asymptotic here. And we talked about why they are. And when we do a strong acid, strong base, I do know that my pH is going to be 7. And if I did not know that, graphically what I can do is I can find where this starts to take off, okay, and where this kind of takes down, and I could basically take these two values and I could pick a ruler and see where the in-between value is, and you can see that the in-between value is a pH of 7. Now, not all acid-base titrations will be a pH of 7, but this one is because it's a strong acid, strong base, as we'll talk when we get to the net ion equation. So the first part is that we're going to have to find the equivalence point. Okay, now the equivalence point is that point where we have the entire base that was added has wiped away all the extra hydroxides. Now the equivalence point is going to be right here, okay? And that is something you need to identify, and that would be number 2, all right, the equivalence point. Now the equivalence point is the place where all the hydroxides, the OHs that I added, have been equal, or I should say equal to the protons that were in the flask. Okay, now how do I know that? Well, graphically there's going to be this asymptotic line that happens during the equivalence point, and that halfway interval between the two exponential increases or decreases is that, okay? And again, you could do that graphically. You could actually find this line and that line, okay, the beginning lines if you had to. And if what you can do is you can actually measure them and find the halfway point. So you can find it graphically. But again, strong acid, strong base will be 7. Now, let's continue on. Now that I know the point, which we call the equivalence point, and you need to mark this, okay, let's talk about the endpoint in the titration. Where did the indicator tell me, okay, where did the indicator kind of tell me that the pH, where the titration would end? If you look carefully, that would be somewhere in this range here. So this would be the endpoint. Now the endpoint is the pH where the indicator changes color. If you weren't using a pH probe like you did last year or some previous titrations, okay, the color change, or the slight color change, that little color change in between would tell you to stop, and it'd be an estimate of the actual equivalence point. The equivalence point will always be this halfway of this asymptotic change, okay? So the endpoint is an estimate. Now, important, let's go back to find the concentration of the acid. Now that I know the equivalence point, the actual place where the hydroxides equal the H pluses, I'm going to go find that, what, volume. And when we do so, and again, my straight edge isn't very good, looks like about right here. So this is 11, 12, 13, looks like about 13.1 milliliters for this graph, okay, represented the volume of base that was needed to neutralize the acid. Okay, so how do I find it? Well, very simple. Convert to liters, 0.0131 liters. You're going to times that by the molarity of the base that we know is 0.03, and that's mole over liter. And you can see, party people, that will give me moles. Now, I'm not going to calculate it, but you get moles. But careful, because we were using calcium hydroxide, what do I know? For every one of these, there's 2 hydroxides. So this will give me the moles of my base, which happens to be in this case, okay, so this will give me my moles of the base. In this case is calcium hydroxide. So I got to convert that to what? total hydroxides. So of course you would have to make a little adjustment stoichiometrically, and now you have moles of hydroxide. Okay, total moles. Remember, this is dibasic, so you got to do something there. So you get the moles of hydroxide. Great. What do we know at equivalence? Moles of hydroxide equal what? Moles of H plus. So now that we have the moles of H plus, what's the whole point? I'm trying to find the concentration of the acid that was in the beaker. So molarity is equal to moles over liter. And in the beaker, there was 25 milliliters, so 0.025 liter, have to be in liters of doing molarity. And the moles of my hydroxide are the moles of my H plus, as long as I figured out what I had to do here to get to this position. I put the moles of H plus here, and I have the molarity of my acid. Now, certainly there's an easier way to do this. What's my initial pH? Okay, well in this case, the pH is about 2. How can I take the pH, which is really an exponent, and convert it to the concentration of the H plus? Ooh, yeah. Don't say negative log. Negative log gets us from the concentration to that exponent. So we got to go backwards. We go 10 to the negative x. So 10 to the negative 2 would give me the concentration of my acid there. Okay, so well, that's a lot easier. Sure, but you might not always have the initial pH. All right, so we have determined the equivalence point. We have the endpoint, which is not the same. The endpoint is based on the value of the indicator changing, and the equivalence point is that exact position. Now, let me talk about this for a second. Very important. If I was to use the endpoint titration, not use a pH probe, would this position be really significantly different from the other one? And the answer would be no. If this is a true asymptote, this position up here won't be any different significantly in volume. So we can use the endpoint as an estimate of the equivalence point as long as you know the difference. Okay, how do we get the halfway equivalence point? Well, if this represents the 13.1, if 13.1 milliliters is this position here, okay, which is the amount of base added to neutralize the acid, how much would it take to get halfway equivalence? Well, that's easy. 13.1 divided by 2. The volume of the base we're dropping stays constant. So find that halfway. So find that position, and it'll be over here somewhere. Put that point and label it. Half of 13, okay, approximately what, 6.5-ish? So that'd be right around here. So put that point. That's the halfway equivalence. Okay. Now I'm saying confirm the initial pH of the titration. Well, once you have your data, how would you do that? Well, once I know the molarity that I just got, I can do a negative log to that to find that initial pH. So again, you can do negative log. So once you find the molarity of the H pluses in the beaker, you could negative log that sucker, and you get the pH of the beaker that should be about what this is. And once you have your file, you can read and see that. That's how you confirm your initial pH. Now, the final pH, and this is very important, the final pH we're trying to confirm here. And how would I do that? It looks like the pH is about 12 here, but how do I confirm that? Well, this is so very important, okay? You have to understand something. If this is the equivalence point, that means all of the volume we added at this point, we annihilated all the H pluses. By adding the hydroxide to the H plus, we made the water. So there's no more H plus left. So that's gone. So everything beyond this position and up represents extra what? Extra, read all about it, extra hydroxide on top of the solution. So how do I get that pH? Well, how many moles of extra hydroxide? And I say extra because at this point it was what? Annihilated. It's a pH of 7, so we're adding extra hydroxide. There's no more H pluses. So all the extra hydroxide that we drop on top of this equivalence point will need to turn into moles. So how much extra hydroxide do we add? Well, we started at 13.1, right? And then we went to 25. So 25 milliliters minus 13.1, it's in my graph, that gives me some value for the milliliters of base that I add. Convert to liters times by the molarity of the base that we used. The standard solution was 0.03. And you're going to get moles of what? Calcium hydroxide. Times that by 2 to get the hydroxide. Then you got to divide by the total volume at this beaker. Well, what was added? 25 milliliters of the base was added to 25 milliliters of the acid, which would be 50 milliliters, and you have your molarity, okay, of the hydroxide. You'd have to convert that to your pOH by doing negative log, right? And then to get the H plus, you subtract from 14, and there's your pH. All the things we've done already. Okay, so that would confirm the final. We had the initial, and on the 4 points of the titration curve, all right, we have the initial pH, we have the halfway, full equivalence, and we have the final pH, and that should be, okay, something you should have determined. Now, we want to determine the percent, so let's get rid of some things here so I can do this. All right, so at this position, don't we have 100% H plus in this beaker, in this position here? Yes, we do. At halfway equivalence, we have 50% H plus. At this position, we have what? 0% H plus. It's been annihilated. Okay, and then everything beyond this position, this would be what? Just extra hydroxide. All right, it's important. So 100% H plus, 50%, 0%, and now just the extra hydroxide. So all we got left is the net ion equation. All right, so how do we do this, party people? Very simple. We take let's look at the reaction. We had hydrochloric acid plus calcium hydroxide makes calcium, it's really a double replacement reaction, chloride plus water. Now, of course, we have we're going to need 2 Cls, 2 here, 2 waters. But this isn't my net ion reaction. This is the overall, and you may need it to think about what we're doing here. But what do we have here, party people? We have a strong acid, which means you have free H pluses. It's a Kardashian wedding. Wouldn't write that. Calcium hydroxide, strong base. Another Kardashian wedding. Not together. Calcium chloride, calcium plus 2. These are soluble. This sticks together. So what do we have? An H plus an OH minus makes water. So essentially, that's your net ion reaction, because the conjugate base and the conjugate acid of a strong acid, strong base are just spectators. That's why the pH is 7. So what I want you to do is go online, look at my website, look to see the numbers. I want you to make sure you number them. So number 2 is the equivalence point. Okay, make sure you put the numbers and show your work. I know this looks like a mess here. Hopefully that helped.